To determine the appropriate wire size and overcurrent protection device, or OCT, for a 5500 watt 240 volts hot water heater, several factors must be considered according to the National Electrical Code, or NEC. Firstly, it's crucial to calculate the ampacity, which is the current carrying capacity required for the hot water heater. The formula to calculate ampacity is power in volt amps divided by voltage in volts. In this case, the ampacity is 5500 watts divided by 240 volts, which equals 22.92 amps. Secondly, the NEC mandates that overcurrent protection devices be installed to safeguard conductors against overloads and short circuits. The OCT should be rated for the maximum continuous current that the conductor can safely carry. According to the NEC, for conductors rated to an American wire gauge or larger, the OCT can be rated up to 125% of the conductor's ampacity. Therefore, a 30 amps OCT would appear acceptable for a 10 American wire gauge conductor. However, due to the high wattage of the hot water heater, which is 5500 watts, it is advisable to apply the 80% rule in this scenario. The 80% rule stipulates that the load on a circuit should not exceed 80% of the circuit's ampacity. To determine if a 10 American wire gauge conductor with a 30 amps OCT is sufficient, we calculate 80% of 30 amps, which equals 24 amps. Comparing this to the calculated load of 22.92 amps, we find that 24 amps is greater than 22.92 amps. Initially, it would seem that a 10 American wire gauge conductor with a 30 amps breaker might be sufficient. However, the 80% rule suggests that a larger conductor and a slightly higher rated breaker are more appropriate for continuous operation to provide a safety margin and prevent nuisance tripping. The 80% dirting factor for circuit breakers and conductors is important in continuous load applications. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. This type of load generates heat within the breaker and conductors, which reduces their capacity to handle current. This is the reason why most electrical codes, including the NEC, mandate that circuits with continuous loads should be loaded to no more than 80% of the breaker's rating to prevent overheating. Given that hot water heaters often operate for extended periods to maintain water temperature, they are generally considered continuous loads. Therefore, it is crucial to apply this 80% dirting factor when choosing the appropriate conductor and breaker sizes. The calculation is straightforward. Divide the total continuous load by 0.80 to determine the minimum required ampacity of the conductor and the breaker rating. In the specific scenario of a 5500 watts 240 volts water heater, we already found the current draw to be 22.92 amps. Applying the 80% rule, we divide 22.92 amps by 0.80, which equals 28.65 amps. This result indicates that the wiring and breaker should be rated for at least 28.65 amps. Referring to the NEC tables for conductor ampacity, we find that a 10 American wire gauge copper conductor with a typical installation like THHN is usually rated for 30 amps in many common installation conditions. While this might appear sufficient at first glance, it technically does not meet the 80% rule requirement as rigorously. A more robust approach is to select an 8 American wire gauge copper conductor, which is typically rated for 40 or 45 amps depending on the specific insulation type and installation conditions. This provides a safety margin above the 28.65 amps requirement. As for the breaker size, the calculated minimum of 28.65 amps falls between standard breaker sizes. The common practice is to round up to the next available standard size, which in this case would be a 30 amps or 35 amps breaker. A 30 amps breaker would comply with the minimum ampacity requirement, but a 35 amps breaker provides additional headroom. However, it is crucial to ensure that the breaker size does not exceed the conductor's ampacity rating, as this could lead to overheating of the conductor. Given the ampacity of an 8 American wire gauge conductor, a 35 amps breaker would generally be an acceptable and safer choice. Always consult local electrical codes and regulations, as they may provide additional guidance or restrictions on conductor ampacity and breaker sizing. Also, it is essential to consider the specific installation conditions such as ambient temperature and the number of conductors in the conduit, as these factors can affect the ampacity of the conductors. In summary, for a 5,500 watts, 240 volts hot water heater using an 8 American wire gauge copper conductor with a 35 amps breaker is a prudent choice. This ensures compliance with the 80% rule, provides an adequate safety margin, and reduces the risk of nuisance tripping or overheating. When dealing with electrical installations, accuracy and compliance are paramount to ensure safety and prevent potential hazards. Always verify the latest electrical codes and regulations and consult with a qualified electrician if needed. The NEC provides specific tables for conductor ampacity based on insulation type and temperature ratings. These tables are critical for determining the correct wire size. For example, the common THHN insulation allows for a higher ampacity compared to older types like TW insulation. Also, the ambient temperature affects the conductor's ability to dissipate heat. If the ambient temperature is high, the conductor's ampacity must be derated to prevent overheating. The number of conductors in a conduit also affects ampacity. When multiple current-carrying conductors are bundled together, they generate more heat. The NEC requires that the ampacity of each conductor be derated to account for this effect. Voltage drop is another critical factor, especially in long circuit runs. Excessive voltage drop can cause a hot water heater to operate inefficiently and potentially damage its components. The NEC recommends limiting voltage drop to 3% for branch circuits. To minimize voltage drop, a larger wire size may be necessary. The type of overcurrent protection device, such as a circuit breaker or fuse, must be appropriate for the application. Circuit breakers are generally preferred for hot water heater circuits because they can be easily reset after a trip. Fuses, on the other hand, must be replaced. The interrupting rating of the overcurrent protection device must be sufficient to handle the available fault current at the installation location. This is typically determined by the utility company. The NEC specifies the requirements for grounding and bonding of electrical equipment. Proper grounding and bonding are essential for safety and to prevent electrical shock hazards. The grounding conductor must be sized according to the NEC tables and must be properly connected to the grounding electrode system. The hot water heater must be bonded to the electrical panel to provide a low impedance path for fault current. The wiring method, such as conduit or cable, must comply with the NEC requirements. Conduit provides better protection for the conductors but is more expensive and time-consuming to install. Cable, such as NM cable, is easier to install but is not permitted in all locations. All electrical connections must be made properly to ensure a reliable and safe installation. Loose connections can cause arcing and overheating, which can lead to fires. Wire connectors must be sized correctly for the wire gauge and must be listed for the application. The installation must comply with all applicable codes and standards, including the NEC, state and local codes. A qualified electrician should be consulted to ensure that the installation is safe and compliant. Permits and inspections may be required for electrical work. Check with the local building department for specific requirements. Regular maintenance is essential to ensure the continued safe and reliable operation of the hot water heater. Inspect the wiring and connections periodically for signs of damage or corrosion. Test the overcurrent protection device to ensure that it is functioning properly. Replace any worn or damaged components promptly. The National Electrical Code, or NEC, provides detailed guidelines for electrical installations, including those for water heaters. It is essential to adhere to these guidelines to ensure safety and compliance. Firstly, calculate the total load of the water heater. This is typically found in the appliance's nameplate and is expressed in watts. Divide the wattage by the voltage to determine the current draw in amps. Secondly, determine the appropriate wire size based on the calculated current draw on the NEC ampacity tables. The wire must be sized to handle at least 125% of the continuous load, as water heaters are generally considered continuous loads. Thirdly, select an overcurrent protection device such as a circuit breaker that is rated to protect the wiring. The breaker size should not exceed the ampacity of the wire and must comply with NEC guidelines. It is often acceptable to round up to the next standard breaker size if the calculated value falls between two sizes, but never exceed the wire's ampacity. Fourthly, ensure proper grounding and bonding of the water heater and all associated electrical components. This is crucial for safety and to prevent electrical shock hazards. The grounding conductor must be sized appropriately and connected to a suitable grounding electrode system. Fifthly, use appropriate wiring methods such as conduit or cable that comply with the NEC and local codes. The wiring method must provide adequate protection for the conductors and be suitable for the environment in which it is installed. Sixthly, make all electrical connections securely and properly using approved connectors and techniques. Loose or corroded connections can lead to overheating and potential fire hazards. Seventhly, obtain any necessary permits and inspections from local authorities before commencing electrical work. This helps ensure that the installation meets code requirements and is safe. Eighthly, consider any specific requirements or recommendations from the water heater manufacturer regarding wiring and overcurrent protection. These recommendations should be followed unless they conflict with the NEC or local codes. Ninthly, document all calculations, wire sizes, breaker sizes, and other relevant information for future reference and for inspection purposes. Tenthly, if you are not a qualified electrician, it is always best to consult with one to ensure that the electrical work is done safely and correctly. Incorrect wiring or overcurrent protection can create significant safety hazards and potentially damage the water heater or other electrical equipment. The National Electrical Code, or NEC, provides specific guidelines for sizing conductors and overcurrent protection for water heaters to ensure safety and prevent fire hazards. The NEC considers water heaters as continuous loads, which means they operate for 3 hours or more. For continuous loads, the NEC requires that the overcurrent protection device be rated at no less than 125% of the continuous load. Here's how to calculate the minimum ampacity and select the appropriate conductor and overcurrent protection device. Firstly, determine the water heater's wattage and voltage. This information is usually found on the nameplate of the water heater. For example, assume the water heater is rated at 5,500 watts and 240 volts. Secondly, calculate the current draw in amps. To do this, divide the wattage by the voltage. In this case, 5,500 watts divided by 240 volts equals 22.92 amps. Thirdly, apply the 125% rule for continuous loads. Multiply the current draw by 1.25. So, 22.92 amps times 1.25 equals 28.65 amps. This is the minimum ampacity that the conductor and overcurrent protection device must be rated for. Fourthly, select the appropriate conductor size. Refer to NEC Table 310.15. B16, which provides ampacity ratings for various conductor sizes based on their insulation type and temperature rating. For example, if using copper conductors with THHN insulation at 75 degrees Celsius, you'll find that 10 American wire gauge wire is typically rated for 30 amps. However, since the calculated minimum ampacity is 28.65 amps, which is very close to 30 amps, it is safer and often recommended to use 8 American wire gauge wire, which is rated for 40 or 45 amps depending on the conditions and the specific table used. Fifthly, choose the overcurrent protection device, such as the circuit breaker. The NEC allows you to round up to the next standard size if the calculated value doesn't match a standard breaker size, but the breaker should not exceed the ampacity of the wire. In this case, since 28.65 amps is the minimum required, you could use a 30 amps or 35 amps breaker. Given that 8 American wire gauge wire is being used, a 35 amps breaker would be suitable because it doesn't exceed the wire's ampacity rating. Sixthly, consider other factors such as voltage drop, ambient temperature, and the number of conductors in a conduit. If the distance from the electrical panel to the water heater is long, calculate the voltage drop to ensure it's within acceptable limits, typically no more than 3%. High ambient temperatures and multiple current-carrying conductors in a conduit can reduce the ampacity of the wire, requiring a larger wire size. Seventhly, ensure proper grounding and bonding. The grounding conductor should be sized according to NEC Table 250.122, and all metal parts of the water heater should be bonded to the grounding system. Eighthly, follow all other applicable NEC requirements and local codes. Electrical work should be performed by a qualified electrician to ensure safety and compliance. In summary, for a 5,500 watts, 240 volts water heater, the calculations and NEC guidelines would lead to the selection of 8 American wire gauge copper wire with a 35 amp circuit breaker. This ensures that the installation is safe, compliant, and provides adequate capacity for the continuous load of the water heater.